Alright, so what we're going to try to talk about real quick here today is take a real quick look at some of the intro into kind of what's going to be adaptation to longer term exercise stress. Again, a lot of this goes back to some of the stuff we talked about previously when we were talking about the idea of kind of training and stress response. Again, any training that's going to lead to a change is going to have to overload the system beyond the level what it's normally used to. Again, going to be very specific to what type of training is being done. So in terms of fibers involved, energy systems that you're tapping into, types of contraction that you're doing. Again, any training that we do, if this training isn't being maintained, is going to be reversible. Again, if any of these things that we're going to try to change with endurance and change at VO2 max, again, this is generally going to have to be a larger muscle groups being activated for a decently long period of time, at least, like it says, they're at least 20 to 30 minutes. And generally, you're going to have to be doing this more than once a week, usually 3 to 4, 5, sometimes more times a week, at least relatively decent intensity, so a little bit over at least that 50% of VO2 max. An average, if you did this type of training and we're doing this over this time period, be looking at sometimes changes up to about 15 to 20% change in VO2 max. Those with initially high VO2 max, again, training age and other things like that, are going to have much smaller increases, and again, you can get quite large increases in those folks that had a relatively low VO2 max to start with. Studies have been done, and we'll talk about one here in just a minute, but genetic predisposition, so your genetics probably play quite a large role in this. Most studies say it's about 50% of what what accounts for your VO2 max is genetic. And again, that's why I've said a number of times in class that to be an elite at anything, generally, especially endurance activities, you have to have the genetics for it. You're not going to train yourself into it if you don't have the genetics for it. So to have a really high VO2 max, probably genetically you need to be there. Again, we've looked at these kind of ranges. We know males are slightly higher than females. We know those things that are more long-term endurance activities tend to trigger these higher VO2 max values in the population. So distance runners, cross-country skiers, as I've said already, tend to have some of those highest VO2 maxes. Again, there was a study called the Heritage Study. It looked at a lot of this and tried to determine what the role of genes was in these kind of exercise changes and the ability to alter VO2 max. What they found, again, is about 50% of VO2 max is heritable. The rest of that is you can modify with training. On average, like I said, about 15 to 20% improvements. But again, depending on training age and other stuff like that, it was anywhere from no improvement to greater than 50%. But again, like it says there, heritability of change in VO2 max is about 47%. And there's definitely a decent number of genes that are going to play a role in altering this with training. So again, the calculation of VO2 max was really kind of looking at cardiac output times that exchange of gases at arteriovenous difference. Like it says there, differences in different populations tend to be due to differences in stroke volume maximums. And again, it tends to be a little bit of both. Again, the shorter duration stuff tends to be more of changes in the heart, so changes in stroke volume and letting that change the heart rate a little bit, where longer term, we're talking years, is going to be a lot more importance on that arteriovenous difference in blood. So shorter term training, like the stuff we could do within the class, would probably be much more related to stroke volume and cardiac changes, where the longer term duration training is going to get you a lot more of those basically oxygen consumption or oxygen utilization changes. And this just kind of shows kind of some of these different things here in terms of VO2 max before training, after a short period of time, after longer term training. You can see much more higher VO2 max increase here. One of the things you can see, short term heart rate max was higher. As you get further along here, it's lower. Stroke volume, lower at the beginning, slightly increased with some training, greatly increased with more, which overall lets us have a higher cardiac output. And again, you can see over a longer period of training that arteriovenous difference, that oxygen consumption was greatly increased further on. But again, overall, this is kind of showing you some of those changes that we'll talk about here in a little bit and how they improve over these shorter and longer term time frames with training. Again, most of these things, if we're going to kind of talk about these, you need at least 6 to 8 weeks of training with multiple sessions a week. Again, less than 6 to 8 weeks is probably not going to be enough of a stressor to bring about big changes. And if you're only doing it once or twice a week, you're going to get too much reversibility happening in between these changes. So you're not going to continue to overload the system. And again, we can see these changes at a number of different levels. It might be changes that we see different when you're fully at rest, where your heart rate might be lower at rest, or we might see increases in the ability to do submaximal work or maximal work. So these trainings changes, these adaptations can help you out at different areas within that level of work. And again, a lot of this is going to depend upon the type of training you're doing, aerobic versus anaerobic, how long, how intense, how often. And as we said, genetics is going to play a big role in this. So here are some of the different things that we'll take a look at. We'll kind of talk about the first few here, but we can definitely see changes in heart size, stroke volume, heart rate, and therefore cardiac output. Again, this is really what we're going to look at with the cardiovascular stuff here, and then we'll come back and talk about changes in muscle, changes in the respiratory system, and metabolic changes with training. One of the things that we see most often, though, is that we're going to see changes in that left ventricle size. The left ventricle, because that is pumping to the systemic circuit with endurance training, you're going to see the most drastic changes in here. What we usually end up seeing on this one is that the wall is going to get more muscular, but the volume also gets larger. So internal dimensions of the left ventricle get increased. If the inside of the left ventricle is bigger, what that means is you can fill it with more blood. And if you can fill it with more blood, what can you do? You can pump more blood out of it. So again, that wall also gets a little bit thicker, but the main thing here is it's not just a thicker wall. Thicker wall without increases in volume is going to be more detrimental. Gives less flexibility to the heart won't pump out as much. With endurance training, you get thickening of that wall with an enlargement of the actual volume of the cavity as well, and that's kind of the key thing when it comes to the cardiac changes with endurance training. And again, on this one, you can see runners and cyclists over time here. You can see increases in the wall's internal diameter, not so much with strength athletes. You can see increases in the thickness, not as much in strength athletes. And then again, overall mass of that left ventricle, much higher in these runners and cyclists, not increased nearly as much relative to control on those strength athletes. And again, the main thing here, resistance training, you will get thickening of this wall, but you don't get much of a change in the volume. Where with endurance athletes, it's a thicker wall with an increase in volume on the inside of this here. So what that means is the heart can more forcefully push out the blood, and it can also push out more. Again, what we don't want is thicker but weaker walls or thicker walls without much change in the volume in terms of long-term adaptations. That is not going to be that useful. One of the things that happens with congestive heart failure is a pathological thickening of the walls of the heart, but no changes in volume, and over time that heart cannot expand as well, and it ends up leading to heart failure over decades pretty much. So what this means, though, is with this higher volume in there as well as a thicker wall, it means that that stroke volume is going to increase, and it's going to increase both at rest, submaximal levels of exercise, and maximal levels of exercise. So that means with each beat, the heart's going to be able to pump out more blood. Why is this important? More blood out of the heart very simply means more blood going to the tissues. More blood going to the tissues means you can deliver more to the muscles, and if you can deliver more to the muscles, those muscles can work at a higher level for a longer period of time before needing to go anaerobic or running out of energy. So like it says here, untrained individuals, it's about 50 to 70 milliliters a beat, increasing to 130-ish during intense activity. In elite athletes, endurance athletes, it might be at rest 90 to 110, and you can get up to over 200 mils per beat on each one of those. What this really means is you can pump out the same amount of output with less beats of the heart, which means you have more in reserve if you are going to require more intensity. So, and this is kind of showing the stroke volume before people train and then afterward here, and you can kind of see, again, the graphs look similar, but increases in stroke volume after training. And again, this means the heart can pump out more blood with less beats, which means lower resting heart rate, lower submaximal heart rates. Again, because you can put out at a steady state the same amount of cardiac output with less beats of the heart if you're pumping out more blood with each beat, because again, output is stroke volume times heart rate. If stroke volume is bigger, it means you can do the same amount of output if you have a larger stroke volume with less beats of the heart. So again, stroke volume means that these endurance athletes, again, during submaximal and maximal exercise as well as at rest, the stroke volume is increased. And what this is really meaning is that with each beat of the heart, we're getting a little bit more blood to the tissues, which means you're going to be able to have a maximal level of output that's higher after training of the heart than what you did before. Even if the ability to beat your heart faster doesn't change. I'll see you next time.